Right, so we're going to finish up chapter 5. And the last section we're looking at is on graphs of logarithms. So generally what we do with graphs is we learn how to sketch them and we look at the transformations. Transformations, what's that? Yeah, transformations are going to be exactly the same as every transformation we've studied. Shifting and the stretching. So first thing I want to look at, we talked a little bit about it yesterday, is what's called the change of base formula. So let's look at an example of something that we can't type directly into the calculator with either the log button or the ln button. Let's say we had, well, let me back up one step from that. Let's say we had 4 equals 5 to the x. Okay, the problem with that is if you do 5 to the 0 power, you get 1. So that's too small. If you do 5 to the first power, you get 5. That's too big. So the answer here is somewhere between 0 and 1. Let's change this to log form. So there's exponential form. Let's make it log form. Okay, we're going to write it in log form. What's the first thing you would have to put down? Log. Word log. And what's going to be my base on that log? 5. And logarithm always equals what type of number? Exponent. Always equals your exponent. And the argument would be whatever was by itself. So that's the answer to the problem. The issue with that is we don't know how to type in base 5. We can do, what 2 bases do we have buttons for? Yep.
Natural and base 10.
So base 10 is your common log. And what's the base on the natural log? E. It's got number 2.718. It keeps going. So let's come back to this in a second. And let's think about this problem a different way. If we could get rid of this x as an exponent, we could make it easier to solve. What would I have to do on both sides so I could move this exponent?
Excluded. I forget the terminology. But it's certainly going to the next.
But we don't know the value, so we wouldn't know what kind of root to do. So right, you have to take the log of both sides.
Oh,
If we take the log of both sides, we get that. Now, what can I do on the right-hand side? Right, I can move the exponent in front of the log, just like that. And how would I get x by itself? Divide each side by log 5. So here is an alternate way to get the answer for x, but it's exactly the same as the other way. But the other way was a lot shorter. I didn't have nearly as much work to write down to do the first one. So let's call this box 1 and call this one box 2. Box 1 is equal to the answer. Box 2 is equal to the answer. So what does that mean about box 1 and box 2?
They're both equal to each other.
Box 1 and box 2 are equal to each other. So log base 5 of 4 equals log 4 divided by log 5. And what we're basically proving right there is called the change of base formula. If you have to take a log, and the base is not a 10 or an e, this is the pattern that you follow. You take the log of the argument, and you divide by the log of the base. And when I say the log of the argument over the log of the base, I mean you could do either type of log. You could use common log, or you could do natural log, and you'll get the same thing. So let's look at this one. Is that what I had? Log base 5, yeah. To type that in on the calculator, we could do log 4 divided by log 5. So, log 4 divided by log 5. And remember what the answer should have been. 0 was too small. 5 to the 0 power was 1. 5 to the first power was too big. So it's going to be between 0 and 1. It's 0.86. Now, let's say you did it with ln's. You can do exactly the same thing. Take the ln of 4, divide by the ln of 5. And you get the same answer. So when you do the change of base formula, you can do it either way. I would just pick one way and just always do it that way. So, any questions on that? So where we're going to use that is we could do something, straightforward like this, just something numerical. But we can also use it if we have to graph something like this. We can't graph a base 3 log directly, but we can rewrite it so that we can. And there's 2 ways we can rewrite it.
How would you graph this?
Well, we're going to do that exact problem right now. So find a complete graph in the domain and the range. Well, before I even think about typing that in, there's something there we should already know the answer to. The range. What's the range? All real numbers. Logarithms have vertical asymptotes. They go up and down forever. So I don't care if it's base 3, base 10, or base 12.4. It's still going to go up and down forever. All right, now to see the domain, it's a little easier if we type it in. But it's base 3. So how can I rewrite it so that it's something I can put in on the calculator? Yeah, please.
Log x divided by log.
Yep. Log x divided by log 3. Let's put that in and see what it looks like. So log x divided by log 3. Let's do 6. All right, so we know that it does keep curving down forever. Like that. And it just keeps going that way. So, what's the domain? Yeah.
Not from 0 to infinity.
Yes. It's a vertical asymptote at 0, and it goes to infinity. 0 to infinity. Good. What else did they want? Find a complete graph, the domain, and the range. Yeah, we're done. Any questions on that? All right, so transformations. They work exactly the same as every transformation we've done all year. I use the letters A, B, C, and D, so that way you can see which one you do first, second, third, and fourth. And let's just label them. What does adding or subtracting inside parentheses do? Yeah?
Shifts it left and right.
Yep. So that's your horizontal shift. Remember, positive is left, negative is right. So that's adding or subtracting inside. How about D? That's adding or subtracting outside. What's that going to do? Yeah?
Vertical shift.
That, yep. So that's your vertical shift. That one is what you would expect. Positive up, negative down. Now C and B are both multiplying. Let's start with B. Multiplying inside the log function. What kind of transformation would that be? Yeah.
Horizontal.
Say it again.
Horizontal.
Can you tell me more?
Stretch.
Stretch. Horizontal stretch.
Vertical.
And what about C? Yeah.
Vertical stretch.
Vertical stretch. Remember, anything with horizontal is backwards. So if you put in a big number for B, like let's say you did log 8x, that's technically a horizontal compression by a factor of 8. Bigger numbers for B actually make the graph more compressed. It's the opposite. Just like positive and negative is the opposite when you shift. So everything about A and B is backwards. C and D is not. If you put in a big number for C, like if you did 8 log x, that's a vertical stretch by a factor of 8. Makes it 8 times as tall.
You said that all for flip.
Yeah. Now what about if B or C was a negative? What do negatives cause the graph to do?
Flip over an axis.
Yeah. Flip over an axis, reflect. B is a horizontal reflection. Horizontally would mean reflecting over the y. C is a vertical reflection. That means reflecting up to down. That would be over the x.
What if you have like a negative A or D, or can you just not have those separate?
Well, negative on D would shift down.
Oh.
Negative on A
Yeah.
would shift.
Yeah, never mind.
Right. Yep, you can have positives and negatives everywhere. So you could have up to 6 transformations if you had both stretches, both shifts, and both reflections. So you could have 6 things. Let's try this one. So how can we get log base 3 of negative x, where the original is log base 3 of positive x? You're always going to be comparing bases that are the same. If you're not comparing bases that are the same, then you're not comparing logarithms that are in like the same family. They have to have the same base. Well, we already know what log base 3 of x looks like. We just graphed it. Where did we graph it? I thought we did. Yeah, right there. So when you put a negative inside the log function, what's it going to cause that graph to do? Flip over what? Flip over the y-axis. So you're going to get a graph that goes like that. That's what the graph is going to look like. So what's going to happen to the range?
Range
Range is
is gonna stay the same.
going to stay the same. You can never change the range. How about the domain?
That'd be negative infinity to 0 now.
Right. It's going to be negative infinity to 0. Okay, so how can we graph that? Let's write that down. So to graph y equals log base 3 of negative x from the original, you would reflect the original horizontally. Reflect the original horizontally. Now find the domain and the range. Okay, so domain. Well, we just said the domain is going to be negative infinity to 0. Do we include either endpoint?
No.
No. You don't include negative infinity because you can't reach it. You don't include 0 because that's an asymptote. And the range, well, that stayed the same. Okay, describe the transformations, domain, range, oh, and the vertical asymptotes. So when you write the equation of something vertical, how does it start out?
Vertical?
Vertical.
It's just x equals.
X equals And where is the vertical asymptote on that graph?
That's 0.
That's 0. Okay, it started at 0. And when you do a vertical reflection, everything gets reflected, including the asymptote. But the asymptote was on the line that you reflected over. Anytime you do a reflection of something on that reflection line, it doesn't move. So the vertical asymptote stays the same. Any question on that? Let's try another one. How can I sketch log of 3 minus x from log x? What's the first thing you would do here?
Reflect over y. If you change the equation.
Okay, how would you change it around?
Take 3 out from the front, so you do negative x plus.
Okay. And now if we follow I guess it's kind of like an order of operations for transformations. Which one do we have to save first?
Oh, true. The horizontal shift of 3.
And that, yes, that makes a difference. So shift, and you said plus is going to move me which way?
Left.
Yep. So shift left 3. And then, what's the negative going to do? Go ahead.
Oh, reflect over y.
Yep, reflect over the y-axis. Or you could say reflect horizontally. And for that one, it is important that we say in that order. Okay. Any questions on that? All right, so how do we graph a log function? Well, the most important thing you want to always find is the vertical asymptote. Because once you sketch a vertical asymptote, the log is either going to curve right or it's going to curve left. And it could have one of 4 basic shapes. That would kind of be the normal shape. That would be a reflection horizontally. Or you could also reflect it vertically. So it would look a little different. But the point is, it's going to curve away from the asymptote. So find that first. If you can find the intercepts, that's good. If you can't, then it's not a huge deal. The vertical asymptote, that's a must. You've got to find that. So how do we find the vertical asymptote? What kind of transformations are going to affect the vertical asymptote? Horizontal ones or vertical ones?
Horizontal.
Horizontal, because if you have a line that goes up and down forever, and you shift it up, it doesn't do anything. So the only thing that's going to affect where the vertical asymptote goes is that part right there. The C and the D have nothing to do with that. Where is the vertical asymptote on a log function normally?
0.
That's 0. So if you take what's inside this box and you set it equal to 0, that will tell you where the new vertical asymptote is.
Alright, we've done something like that before.
Yep, we did it with square roots. So take your argument, which was inside that red box, and set it equal to 0, and solve. That will tell you the new location of the asymptote. And if we want to try to find the intercepts, we can. If you want to find the x-intercept, what number do you plug in?
Oh, why? No, right.
What number?
0.
0. And you plug it in for the y. What if you want to find the y-intercept? Put in 0 for the x. So x-intercept is when y is 0. The y-intercept is when x is 0. Now, you're probably going to need a few more points just to get an idea of the curve. I would say probably 3 is enough. But remember, it only curves in one direction. So if your graph looked like this, and you tried plugging in an x value of like -1 or -2 on the table, what would happen? Yeah, you get an error because you tried to go and plot points where the graph doesn't exist. So once you find the vertical asymptote, just pick one point. If the point you plug in works, then anything on that side of the asymptote will work. If you get an error, then you pick the wrong side. Try the other side. And the way you can kind of figure out what you should be plugging in is the argument should be positive. So if I was trying to figure out where the asymptote is there, it's at x equals 1. And try plugging in a number like -10. If I plug in -10, I get -10 minus 1 is -11. I can't take the log of -11. So the number that I picked was on the wrong side. Try numbers on the other side. Try like +2. If I plug in 2, yeah, I can do that. But the calculator will help speed up plugging in points a little bit. Since you only need 2 or 3 of them, it doesn't save you a ton of time, but it saves a little bit of time. Let's try a switch. So log base 2 of 3x plus 5. If I want to use the calculator to get some points for me, I need to write that in a way that I can type it in. How would I rewrite that?
Oh, 2 together with the base, right?
Yes.
ln log n.
Say it again.
ln.
Okay.
Of the 3x plus 5.
Yep.
Over ln 2. Does it work if you do like one of each or no? Or would that like?
No. Got to stick with the same one. Yeah, that's fine. So that's what we'll.
Does it have to be ln or could those just be log?
Could be a log, yeah. Either way. So ln 3x plus 5 divided by ln 2. Divided by ln 2. All right, so we got that. Let's find the vertical asymptote. The nice thing about logs is only one asymptote and it's always vertical. You don't have to worry about anything else. How do I, Christian, how do I find my vertical asymptote?
You said y, but you said the argument to 0.
Okay, what's my argument in this case?
3x plus 5.
Whoops. So set 3x plus 5 equal to 0. That's all. So there's your vertical asymptote. All right, let's graph that. So that's good. So -5/3, that's -1 2/3. So just graph that the best you can. Okay, so there's my vertical asymptote. And now I need a couple more points. Well, I already got it typed in, so I can get to the table pretty quickly. And let's pick a number that's bigger than -1 2/3. What's a number that's bigger?
-1.
Okay, we could do -1. Right, let's do a couple more. What would be another good one? I would do 0 because that's the intercept. And I would do like two positive ones. Let's do 4 and 10.
Okay.
So we picked values that were on the right side because it curves to the right. If you picked one that was on the left side, you get an error because it doesn't curve that way. Okay, so we've got -1, 1. We've got 0, 2.3, roughly 4, 4. 1, 2, 3, 4, 1, 2, 3, 4, and 10, a little about 5. And remember, it's going to curve and get very steep near the asymptote. It's going to come up. Kind of do something like that. All right, so we've got the vertical asymptote. It's over there. How about my domain? Yeah.
From -5/3.
Yeah. From -5/3 to infinity. And my range? All around numbers. Right. So domain, range, and asymptotes. And a sketch. Any questions on that? So that's the idea of sketching. They all work out pretty much the same. You just set it equal to 0 and start by finding your asymptote. All right, is this the last? Yep, last one. So we're going to look at a problem now, to be a word problem, that involves the intensity of an earthquake measured on what's called the Richter scale. So the Richter scale has a few different variables in it. Most of the time, these variables are given to us, so we don't have to worry too much about it. R is the intensity. So like if you hear like they had a magnitude 3.4 earthquake, that's the R. That's the number that most people kind of have an idea of how bad an earthquake is based on that R value. A is the amplitude of the vertical ground motion in micrometers, however they measure that. But if you imagine like you took a rock and you drop it, go up above a pond and drop it in there. Well, it's going to send a wave out in the center. That's just like an earthquake. That wave has a height to it. It might only be like half an inch above the water if it was just like a small rock. If you drop, a huge rock, you could get waves that are feet tall. So A is the amplitude of the vertical ground motion measured in micrometers. T is what we call the period of the wave. So we'll study more about that when we do trig. But here's a wave. A period of the wave is basically the distance from one point to another corresponding point. Like, say, from the height here to the height here. That distance is called the period of the wave. Some waves have a very long period, some are shorter. But that's the idea of the period. There's a little bit more to it, but that's basically what it is. You might have heard the term wavelength too, like a wavelength. That's kind of what I'm describing there, but it's tied in with the period. And B is a factor that accounts for the weakening of the wave. So imagine you drop a rock like on sand versus water. Well, if you drop it on sand, the rock's going to hit. It's probably just going to the energy just kind of dies out. So depending on the type of ground where the earthquake happens, controls how bad it is. And that's our formula. So measured on the Richter scale, you could have earthquakes that have different intensities. By the time you get to like a magnitude 5 or 6, that's starting to get pretty bad. And then like 7 and above, it's really bad. Does anybody know the difference in the intensity?
Like 10 times or something.
It's a factor of 10. That's what we're going to look at. Every time that you go up to another number in the Richter scale, it's a factor of 10 times as much. So if you're comparing a magnitude 6 to a magnitude 3, that's a difference of 1,000 in the, I don't know what you call it, the intensity of the earthquake. So it goes up by a factor of 10. And we're going to see why. Why is it 10? Well, it has to do with the fact that there's a log in the formula. So it says, at the early stage of an earthquake, the amplitude of the vertical ground motion was A, when the earthquake was just starting. At a later stage, the amplitude of the vertical ground motion became 10 times as much. So now it was 10A. I want to know, when you multiply the vertical ground motion by a factor of 10, what does that do to the intensity? Well, we kind of already saw, when you go by a factor of 10, the intensity goes up by 1. Well, let's see. We're looking for some type of change. What operation in math do you use when there's a change that needs to be calculated? Change between two values. Subtraction. If I said, your test score was a 90 the first time, and it was a 83 the second time, what's the change between the two? You'd subtract. So we're looking for a change. So we're going to subtract two things. If you want the change to be positive, you should subtract. You should have the bigger one minus the smaller one. Well, I know at some point, at the later stage, it was a bigger amplitude of ground motion. So this part is going to be the later stage minus the early stage. That's the idea of what we're going to do. But we need to do that with the formula. So let's figure out what the earthquake formula would be at the later stage. There's our formula. So it's log A over T plus B. So log. What do they tell us the A value is at the later stage? 10A. Over. What goes in the bottom? T. We don't know the period of the wave, so we'll just call it T. And what goes on the end? B. So we have that minus. Now let's set it up for the early stage. Log. What's my numerator in the early stage? Just A over T. And then what goes on the end? Plus B. There's two things here that are not changing in this problem. The B value, we're assuming the ground is the same type of ground before, at the beginning and the middle of the earthquake. And the period of the wave, we're assuming stays the same. Only thing that's changing is the vertical ground motion. Okay. So let's simplify that and see what we get. What would be the first thing I want to do there to simplify that?
Remove the like terms. It would be since you're subtracting it from itself.
Yeah, I would distribute this negative out because if you do that, the b's are going to cancel. So then you're going to end up with log 10a. I don't want my L's to look like 1, so I'm trying to be careful. But log 10a over t minus log a over t. The b minus the other b cancels out. So that part's good. All right, now let's look at this. We have division inside this argument. Let's split it apart. How does division split apart? Subtraction. So log, we're going to subtract them. What's my first argument? 10a. And what's my second argument? T minus. And whatever we do to the second one, we're subtracting the whole thing. So we're going to split it again, but remember, you're subtracting all of it, even if you split it. How is log a over t going to split up? Log a minus log t. Now, what would we want to do with that step? Distribute the negative again. So the first part stays the same. And what does the second part become?
Negative log a plus log t, so it just cancels.
Negative log a plus log t. So what cancels out?
Log t's.
The log t's. And that should cancel out because the t was the same at the beginning of the earthquake and the middle of the earthquake. So the t should not have an effect on this.
Sorry, what did you distribute? Or did you just remove the parentheses?
I removed the parentheses by distributing the negative. All right. So now we're down to just one letter. We have log 10a minus log a. What do you think I should do with those two logs now?
Can you combine them?
Let's combine them back together. When I recombine it, I'm going to have a single log. And I had subtraction. How does subtraction combine back together? Division. So it would be 10a over a. So now what happens there?
You just get 10 over 1.
A's cancel.
Oh,
And now we have the log of 10, which is just a number. What's the log of 10? 1. So what that means is if an earthquake has whatever the vertical ground motion becomes 10 times as much in a later stage, that's an intensity difference of 1. So that proves what I asked you. Do you know what happens when you go from like a magnitude 3 to a magnitude 4? When you increase by 1, it's 10 times the ground motion. Proves it. Any question on that? Alright, so that last problem is actually a good review of log rules and a little bit with distributive property because it had a lot of different parts to it. Alright, so we already did the 293, that was last night. So for tonight, it's the page 301. So I think it's 11 questions. Yeah, what did you say?
are you gonna change this one up at all? Because yesterday you said you might, I don't know.
Let me double check it and see if there's anything there that's not good. I think it's okay.
dip out on these.
Yeah, I think that's okay.
Yeah.